This lecture is all about Earth. It's kind of broken into two parts, so we're going to talk about what makes Earth unique in the second half of this mini lecture, and then the first half we're going to talk about the layers of Earth. You've probably learned about this at some point before, so we're looking at the crust, the mantle, the outer core, and the inner core. It's a really bad analogy, but basically we can think of Earth as a giant hot pocket. It's got a crust on the outside that's kind of flaky. It can break easily. It's got a mantle underneath of that, and then it's got its scalding hot core of that hot pocket. So the conclusion is that Earth is one giant hot pocket. So how do we know what's actually inside Earth? If you want to know what's inside of an egg, you can take an egg, you can crack it open, take that smiling, happy egg, crack it open, turn it into a sad egg, but that helps you look at the layers of the egg. Obviously, we can't do that with Earth. We can't take all of Earth. We can't crack it open like it's an egg to look at what's inside, like on the right side here. So how do we know what's inside? You might guess that perhaps maybe we have dug a hole and we've dug a hole to a certain depth, and that has let us know about what's inside. But in terms of the biggest hole that we've ever dug beneath Earth's surface, it's really only 7.6 miles. That's it. It's more than 4,000 miles down to the center of Earth, so we've barely scraped the surface in terms of being able to see what's inside of Earth physically. So what that means is that we have other ways of interpreting and trying to hypothesize and use the scientific method to determine what's inside of Earth. So the deepest hole we've ever dug, again, basically is 7.6 miles. It's called the Kola Super Deep Borehole, but I put a link to a video if you wanted to learn more about it. Basically, it was a Russian program where they spent about 20 years using a drill to dig a hole down into the earth to try to determine what it's like at that certain depth. They couldn't go any deeper because they already spent a lot of money, and then the drill bit, what they were using to dig into the ground, it kept melting. So they couldn't actually dig any deeper. All right, anyway, but there's a YouTube video if you want to learn more. It's about 4 minutes long about the deepest hole that's ever been dug. So how do we actually know that Earth has layers? So the way that we know that Earth has layers is because of earthquakes. So we'll get to earthquakes next week, but an earthquake is a movement of a tectonic plate. And when a tectonic plate moves, it generates a form of energy that we call seismic waves. So seismic waves, if Earth did not have layers, the diagram on the left here is showing you what the pattern or the motion of those waves would be if Earth didn't have layers. So an earthquake would happen up here at the top, and then basically those forms of energy or those waves would just travel in a linear line away from that earthquake through the interior of Earth. That doesn't happen. So what that means is that we have layers underneath the ground. We have layers because the seismic waves or the energy when an earthquake happens, sometimes they shoot off in different directions. So they don't travel a straight path. They refract a little bit. Sometimes they go faster and then they slow down and then they speed back up. What that means is that basically it's going through different material. A good analogy for this is that if you're hearing my voice now, my voice is traveling through air. But if for some reason I was trying to teach this class underwater, in a pool or something like that, if my voice was traveling towards you, it wouldn't travel towards your ear at the same speed because my sound is traveling through water versus air. So that difference in speed is what we also observe with seismic waves or earthquake waves traveling through Earth's interior. Sometimes they travel slower, sometimes they speed up. And what that means is that there's different material interior to Earth that causes those waves to kind of change speed or velocity. So how we're going to start is from the inside and work our way out. So we're going to start at Earth's core. A good analogy for looking at Earth's layers would be a hard-boiled egg. So we're going to start with the yolk and then work our way out to the shell or the crust of Earth. So Earth's core is at the very center of Earth. There's two parts of Earth's core. There's the outer core and the inner core. If you want to get really specific, geologists think now that there is an inner core. If you're interested in that, you could look it up. So we think there's actually more layers than just outer core and inner core now at this point. But the difference between these, the outer core, or the inner core is the center of Earth. It is solid, so it's about 4,000 miles down beneath wherever you are on Earth, and it is solid. The outer core is outside of that. So we got the inner core, and then the outer core is outside of that. It is molten, so it is liquid. It moves, it rotates, It generates our magnetic field that we have on Earth, so it's liquid. So that's the main difference is the properties. One is liquid, one is solid. In terms of other things, though, the only other kind of important point about the Earth's core, at least for this point in the semester, is that it's made of iron and nickel. So both the outer core, the liquid one, and the inner core, the solid one, are made of the metals iron, Fe, and then nickel, Ni. If we work our way out to the mantle, that would be our next outermost layer, just beneath Earth's crust. So in terms of composition, it's the thickest layer of Earth, and there's a couple elements from the periodic table that it tends to be made of more. So 90% of Earth's mantle is oxygen, which is O here. Si is silicon, the element silicon. Mg is magnesium, and then Fe is iron. So that's Earth's mantle, thickest layer. We'll talk about Earth's mantle a lot next week when we're talking about plate tectonics and the different types of plate boundaries and how continents can move. Lastly, if we work our way out to the outermost layer, the one that you interact with on a daily basis, that would be Earth's crust. In my egg analogy, basically this is the shell of the crust. It's very thin compared to the other parts of Earth, but obviously it's what we interact with on a daily basis. So when we're looking at Earth's crust, it's solid rock, so it's usually made of 75% oxygen, O, and then silicon, Si. Those are the two main elements that we find in Earth's crust. It differs a little bit depending on where you are, which we'll talk about later on. But Earth's crust can be continental, so that would be, if it's on a continent, it's continental crust. It can also be oceanic. If it's on the bottom of the ocean, then we call it oceanic crust. So we break the crust into two parts. If it's under the ocean, oceanic crust. If it's on land, continental crust. Continental crust tends to be thicker. If we're looking at our diagram here, it tends to be thicker, and then oceanic crust is much thinner. It's about 7 miles thick on average, whereas continental crust is usually about 20 miles thick on average, or upwards of 50 miles thick, depending on the location. All right, so we already talked about its continental or oceanic in composition. If we put all that together, we're looking at the inner core is what we started with, solid, iron and nickel. Outer core, liquid, iron and nickel. We've got the mantle, oxygen, silicon, magnesium, and iron are the elements in that. And then we have our crust on the outside. So we're almost done with the layers. We just have to add a couple more. The crust, mantle, outer core, and inner core we know about because of earthquakes. So again, those seismic waves or the shaking that an earthquake produces causes waves to either speed up or slow down in different layers. We can also categorize rock based on its behavior. So some rocks are what we call brittle. Other rocks are what we call ductile. Brittle means it breaks easily. Ductile means something can change and change shape and kind of morph and move a little bit, almost like peanut butter. So it's still a solid, but it still has a little bit of ability to kind of move and change shape. That's what we would call ductile. So rocks can behave brittle or ductile, meaning they can move easily, or they might break easily. So the layers that we use for this, talking about the behavior of rock, is lithosphere and asthenosphere. The lithosphere is just the crust, all of the crust, plus the upper mantle. And then the asthenosphere is underneath of that, and that's weak mantle rock. So again, the best way for you to think about it is it behaves like pudding or peanut butter. So it's a solid, but it can change and move and morph easily. All right, so this is kind of getting into plate tectonics, but the lithosphere is tectonic plates. The asthenosphere is what tectonic plates float on. So if we're looking at our diagram here, we have the lithosphere is kind of on the uppermost layer of Earth's layers, and then we have the asthenosphere underneath of it. Lithosphere is rigid, it breaks easily. Asthenosphere is more easily movable, bendable, morphable. It can change shapes. Okay, so all of that is put together on this figure here for you with all of the layers. So if you're looking at the week 1 part 4 quiz, you should be able to answer questions 1 through 5 at this point. Once you answer those 5 questions, then you have answer 6 or question 6 on the quiz. You're going to match blanks A through H to the appropriate term that you see here on the diagram. So you'll probably want to pause this and then look at that diagram and then answer the questions on there. Before we get to why Earth is unique, I just want to mention one more thing about Earth's properties, and that's called the geothermal gradient. If you break that word down, geo means rock, thermal means heat. So the one other thing that I want to point out is that if you dig a hole, like the Kola super deep borehole that I was talking about, the deepest hole that's been dug on Earth, the deeper you dig beneath Earth's surface, the hotter it gets. That's called the geothermal gradient, and it's the idea that as you dig deeper beneath the surface, it gets hotter and hotter and hotter as you get towards the interior or the center of Earth. Just to put some numbers to that, so if you dug a hole every kilometer deep that you dug, the temperature increases by about 25 degrees Celsius. Just to put that into US units, 75 degrees Fahrenheit, increase in temperature for every mile that you dig deeper beneath the surface. So that's on average. Some places are hotter, some places are colder, but as you go deeper beneath the Earth, it can get quite hot. So there's some underground mines all across the globe that have temperatures of 120 degrees Fahrenheit because they've dug down deep enough that they have hotter temperatures at that depth. Just to show you what it looks like, here is the temperature in degrees Celsius on your x-axis from 0 to 5,000 degrees Celsius, and then you have depth on the y-axis, so the surface is 0, and then the inner core, the center of Earth, is about 6,000 kilometers beneath us. So based on this and looking at this graph of this geothermal gradient, you should be able to answer question 7 on your quiz. Our last small unit that we're going to finish up here is why is there life on Earth but not on other planets that we know of at this point in time. This could change in the future, but let's talk about why we have life here on Earth and we don't have it on other planets that we know of. So why is there life on Earth? The first reason is that there's liquid water in abundance on Earth. This is not unique to Earth. There's been evidence of water found on other planets, but we have an abundance of liquid water here on Earth. Even on Earth, we have cold liquid water, we have very warm liquid water that's almost at boiling point. In both of those extremes, we still have organisms that are adapted and evolved to live at those temperatures. So as an example, here's some hydrothermal vents. They're down on the bottom of the ocean floor. Hydrothermal means they have hot water that comes out of it, and these kind of white thingies are tube worms that grow on hydrothermal vents down at the bottom of the ocean. The image on the right side, that is Grand Prismatic Spring. That's in Yellowstone National Park in Wyoming, and the colors that you see from this Grand Prismatic Spring is just different bacteria. So different colors equals different bacteria that can live and thrive in different temperature water. And the average temperature of Grand Prismatic Spring is about 170 degrees Fahrenheit. All right, so there's life on Earth because we have liquid water. There's life on Earth because we have gravity and a protective atmosphere. So again, we'll get to it later on in the semester, but there are certain layers of our atmosphere that blocks harmful radiation, like X-rays and gamma rays and ultraviolet rays, some of the ultraviolet rays that reach Earth's surface. Without that protection of our atmosphere, we would either have higher rates of mutations in DNA, we would have higher rates of skin cancer and other types of cancer, but our atmosphere does a job of protecting us from a lot of that radiation or rays from the sun. There's a general rule that basically if you have a larger planet, it's going to have a more gravitational pull, and it will have a thicker atmosphere. And that'll come back into play in questions that you're going to answer in a second. All right, we know life is on Earth because we have the biosphere. One unique aspect of Earth that has led to the evolution of life is the greenhouse effect. So the greenhouse effect has to do with climate change, but it is a good thing. It is the idea that any energy from the sun that hits Earth or bombards Earth will get reflected back up into the atmosphere, and our atmosphere can trap that heat or trap that energy. And by doing so, it heats up Earth's surface. So if we didn't have a greenhouse effect, the ability of our atmosphere to trap heat in it, on average, Earth's surface would be about 0 degrees Fahrenheit globally. Since we have a greenhouse effect and our atmosphere is able to trap heat and able to trap energy and heat up Earth's surface. The average temperature of Earth is about 59 degrees Fahrenheit. So the greenhouse effect is a good thing. It is what has led to there being a biosphere in the first place. All right, Earth is also unique in terms of there being life on Earth due to our magnetic field. We have a magnetic field, so basically, Earth is like one gigantic bar magnet with a north and a south end to it. And there's these imaginary flow lines basically that go from the north to the south magnetic pole. What that's generated by is movement of the liquid iron and nickel that's down in the outer core that we just talked about. It can flow, it can move. And when you have flowing iron and moving iron and nickel, you can generate a current and you can generate a magnetic field. So, due to our outer core rotating, it generates a magnetic field. And basically, the magnetic field is another way of allowing our atmosphere to stay in place and another way of protecting Earth from things that would bombard it from outer space. All right. So, based on those 4 reasons why Earth is unique, you have 4 questions. That's not 4 questions, that is 6 questions. You have 6 questions basically to finish up your quiz here. So, you got questions 8 through 13. For this, basically, you're picking which one, warmer or cooler. So, as an example, if Earth was farther from the sun, then the planet would be cooler, which would be your answer there for question 8, because now Earth is much farther from the energy source, from the sun source. So, if Earth was farther from the sun, then the planet would be cooler. So what you need to do is basically go through questions 9 through 13, think of the same thing, and then answer which of the options from these 2 columns is more correct based on what we just talked about. All right, if you want some kind of take-home messages, Earth is a planet uniquely suited for life due to all the things that we just talked about. The biosphere, it's got liquid water, it's got a magnetic field, it's got a greenhouse effect due to the way our atmosphere is. And then we also have the layers that we talked about and the geothermal gradient. So we have a heat source internal to Earth, we have a heat source external to Earth, and all of that works together as Earth spheres interact to make Earth a planet that is uniquely suited for life.